Hello, thank you all for coming and thank you for the introduction, Aisha. As she told you, I spent this summer so fortunate getting to study Mars. It was an amazing experience. Mikki and I, basically, we were wanting to look at the geologic context of olivine on the surface of Mars, and I'll tell you why that's important here in a moment. Okay. So, not a lot of people, there's not a lot of information on Mars yet, surprisingly. What we do know, however, is that the planet Mars is considered a basaltic planet. You could think of the lavas and magmas that you see on the surface of Hawaii, for instance. They're very smooth flowing, they're very dark, and they cool just like at the surface really smoothly. And that's an image that I have up right there. It is actually an image of the Kilauea volcano in Hawaii. I guess it is Hawaii, really. And so an interesting point about basalt is that you can find olivine in it, which is kind of a unique mineral for several reasons. I have an right there for you that kind of shows what olivine looks like. It has kind of a green-yellow color. It's kind of cool. So what makes olivine important on Mars is two important factors. So when you look at Bowen's reaction series, it compares not only the temperatures at which minerals cool, but it also tells you a little bit about weathering and its resistance to weathering. So for olivine, we can see it up here at the top. This is under the category of basically it cools at the earliest out of a magma chamber. So we don't often see it on the surface of Earth because we have a lot of continental crust it has to get through, and so by the time it reaches the surface, a lot of times the olivine has already crystallized out. So it's a pretty unique environment that we see it appear here on Earth. And another important factor is its lack of resistance to weathering. So we have a lot of water on Earth, and usually interaction with water will break it down, and you lose a lot of the olivine crystals that you originally had. So basically, by having seen olivine on Mars, which we've detected through remote sensing techniques, it tells us a little bit about the Mars environment that's a bit different from Earth. So let's talk about Mars a little bit. The geology of Mars is pretty complex. We do know it's a basaltic planet. It has quite a topographic variety. I've included a topographic map here for you. This is the whole planet Mars. And we have the northern region is the lowlands and the southern region is the highlands, which you can see by the colors. The dark blue and green are the lowest topographies, and yellow and orange and white are the highest topography. Okay, so we can kind of see that there's some variations there. We also have characterized olivine on Mars by using samples that we have here on Earth, and we just compare them basically using the remote sensing techniques. We characterize the olivine based off of a ratio of magnesium to iron, which is the content within olivine, okay? And we call this the Forsterite value or Faux type. So I'll be referring to these as Faux types from now on, but this is that ratio of magnesium to iron. And the way that the scale works is that the Faux 1 values are the most iron-rich of those, and the Faux 91 are the most magnesium-rich. So we have a scale here that we're looking at. So we chose So we had several questions based off of this unique environment that Mars has. We're seeing olivine. We want to know why. We want to know what type of environment it's in. So our questions were really how are the Faux types expressed? So that scale we were talking about, the ratio scale of iron to magnesium-rich olivines. We wanted to know if those exist in certain types of environments, certain types of landforms, or which ones were deposited first. So we basically wanted the geologic context of it. We also wanted to know what the olivine abundance, composition, and the geologic context tell us about both magmatic processes and the geomorphological or weathering processes, because again, olivine exists in that kind of unique environment. And lastly, we just wanted to see if our results can kind of fit into what everybody is learning about Mars currently. We wanted to see if we could kind of contribute to the greater picture. So we chose our study area. It's called Terra Sirenum. It's part of that southern highlands I pointed out on the topographic map. We chose it for several reasons. We needed an area with low dust coverage because we were counting on these remote sensing techniques that use like thermal values, and it counts on basically being able to see the surface. And dust can skew that. So we wanted really good data that wouldn't be altered by dust. So part of our project was deciding on an area that didn't have that, and this is part of the area. We also wanted an area that had kind of a topographic variety. So if you can see over here on the right, this is actually our full study area. It's about 50 kilometers across, about 50 by 50. And as you can see, there's tons of craters, and then we had the Sirenum fosse, which is a giant trench that's related to like the normal fault systems in the area. So we had a lot of landforms we could work with. So first, we mapped the olivine. We worked in the software JMars, which if any of you have used ArcGIS before, this is the Mars version of it. So it's really cool. We used these polygons that you can see up on the top right. They're these teal-colored things. Those are all the olivine detections that we found in that corner of the map. Okay, so some of the instruments that we used were the tests. It's a thermal emission spectrometer, again, counting on that heat. And that told us what type of photype it was, so again, what kind of composition the olivine was. And then we used THEMIS data for two different reasons. We used the daytime in order to see the extent of olivine. So we used these false color images where magenta and red kind of told us that that's where the olivine is found. So, and I'll show you how that compares to TESS here in just a moment. And then we also used Mars Orbiter laser altimeter to investigate the topography and elevation. And we used the Mach camera and high-rise camera, which are just these really nice high-resolution cameras that can get up to like centimeter scale. It's gorgeous. So we were able to pull up a lot of that data, basically just to get an idea of what was going on in the surface. So here's kind of an idea of what I did all summer. This is kind of a summary of what it looked like. So we started off with test detections, and we pulled up these layers that we'd impose on the map. And so it showed us these pixels, and what we were looking for was red, magenta, and purple, which indicate olivine. Okay, so what we did was we pulled up the faux type maps for each type. So in this particular location, faux 53, we were able to detect some olivine. So after that, we pulled up the THEMIS, which gives you kind of a better spatial resolution. As you can see up at the top left, that's a little bit difficult to tell exactly where the olivine is. I mean, you've got really kind of a poor spatial resolution on that. So as you can see on the THEMIS daytime false color image, we found a whole bunch of magenta within this crater. So this was great. It shows the TESS and THEMIS are agreeing. So then we went to create the polygon, and this crater happened to be about 15 kilometers across. So we're talking pretty big scale here. And we labeled it based on its photype. So this one was a faux 53, which on the scale of Forsterite values is kind of in the middle. It's kind of magnesium and iron, kind of an even ratio. Then we looked at the THEMIS nighttime thermal inertia in order to see where the area was consolidated, if we have any bedrock, or if it's just like loose materials such as sands and that type of thing. So it was kind of cool to see that this crater, right where we were seeing the olivine, happens to be high thermal inertia. So we're looking at probably some pretty close to bedrock or consolidated materials. We also wanted to look at the context of the detection. So this is that crater, and right next to it is another one that it's actually compounded upon. So you can kind of date it and say that this one relatively is younger than the one that it's underneath. So if we found a different type of photype value there, we could compare magma evolution. And finally, we looked at the high-resolution images. This one is a tiny little speck inside of that little gray square. It's amazing how close we could get on these, but you could tell that the surface isn't as smooth as it appears in other images. So this kind of told us the geomorphological side of things. We got some really cool results. We found olivine primarily in unconsolidated materials, which I'll tell you why that's so cool in just a moment. And we also found it in crater basins, crater rims, and ridges primarily. So why is it important that we found olivine in unconsolidated materials? Well, there's kind of two factors that could potentially have influenced the types of formations, the unconsolidated materials. I have a rippled trench here. You can see those ripples just running kind of perpendicular there. So these could either have been driven by wind or water, was kind of our idea. So which one would it be? Well, because we were able to find olivine in there, and because we know that olivine doesn't tend to exist in watery areas, in areas that are abundant in water, we could pretty much safely narrow it down to wind or a mechanical type of weathering to eliminate water as a big factor in this area. by having that type of data. And we also found that the area is primarily the Fo-68 and Fo-53 magmas, which of course this is the most superficial stuff, so it could have been the most recent, and so that's why it could be the greatest coverage, but we weren't entirely sure yet. The Fo-91 and Fo-1 values are very hard to find, which, I mean, if you think about it, to have that extreme of composition would be very difficult. And then we also found that Fo-68, which happens to be the primary olivine we detected, was also the most consolidated. So we kind of found a little bit of a patterned distribution of Fo types, and so I've summarized them here a little bit. The most iron-rich, which are like the Fo-1, Fo-18, were found primarily in crater rims. We found in ghost craters, we found primarily Fo-39 and Fo-53, which are like the median values. And what's important about this is that ghost craters are created by lava flows that flowed over the old craters, so we can temporarily get kind of a magma evolution story from that. And then finally, the most magnesium-rich olivines, which are like the Fo-91, Fo-68, we found them in ridges, crater basins, and old crater rims. So this kind of appeared to be the older type of magma. So I've kind of created a little diagram here for you to kind of give you an idea of where we were seeing these things, just because it's easier to see a visual. We were just looking at a cratered environment, so it made it easier to kind of get an idea of what we're looking at stratigraphically and so on for this area. Again, it shows that Fo-91, Fo-68, which are the magnesium-rich, are kind of lower, and then Fo-53, Fo-39 would fill in this crater. So it kind of gives you an idea of which one was first. So do we have an explanation for this? It's kind of a complex thing we have going on. We are seeing, in our primary results, we're seeing that there's a transition from magnesium-rich magmas to the more iron-rich magmas. So we were curious why this is happening. There is one important factor that Fo-1 and Fo-18 aren't quite fitting into this, so that it could be another explanation. But basically, we are starting to see results that are supporting the magma overturn model. And this was proposed in 2003 by Elkins-Tanton, and it's this idea that there's a gravity-driven overturn of crust. So Mars works a little differently than Earth. Mars has kind of a thinner crust, and what the thought was is that the crust here, up in the top right, was actually rotated based on a gravity-driven crustal overturn, which could be driven by a gradient difference in the types of magmas we were seeing, because there is magnesium-rich crust and then iron-rich mantle. So if this was true, it would rotate around and it dragged up the iron-rich materials on top. So this is an idea that has been proposed. Of course, it's based on a lot of assumptions. So what we propose is that we do more studies on this, more thorough studies. We were a little bit time limited on the area we were able to do, so I propose kind of doing a full study of most of the southern highlands, because that gives you don't have much dust coverage there. And in order to get a better idea of the hydrological factors in the area, we'd propose chloride studies or phyllosilicates, which are kind of like the clays that are left behind by water. I mean, we know that there was water there at some point, but our study is too recent, basically. Olivine is too recent in order to tell us much about the past. So we'd need these other studies to tell us more of a historical story of water. And we just propose basically that we just continue this mapping and work with others who are doing similar things. And in summary, our distribution patterns are better understood, which is one of the things we wanted to do. We also wanted to understand patterns, which we talked about, that we're thinking it's more mechanical weathering rather than hydrological. And our information does actually contribute to the overall knowledge on Mars right now. So that was a pretty cool finding. And I just wanted to take a moment to acknowledge everybody who has made this summer possible. It has been fantastic. So, thank you.
Great job, Molly. Questions. I'm going to go to Glenn here real quick.
So, very nice presentation and work.
Thank you.
If you were to go and pick up a piece of lava that was extruded from Kilauea, what would be the faux content of the olivines?
Oh, that is a good question. It's not likely to be strongly one or the other. I mean, we do have a more felsic crust on Earth, so I would think that we were kind of closer to the iron enriched, but it is a basalt. I don't know. I mean, that could really be anything because Hawaii is unique. I mean, Hawaii is from a hot spot, so it's not the typical volcanism we tend to see. So honestly, I'd have to look that up, but I mean, I could probably swing both on that. I would think more magma because it's basalt, but.
I was just curious how much uncertainty there is in terms of determining the photype. So you're looking at this imagery and stuff. So how much wiggle room is there, or do you even know?
There's a lot. If you look at different, let's see, where we were at. If you look at the difference between the test that's up here in the top left and the Themis, you can see that there's a really poor spatial distribution right there. That's telling us that it's FO 53, but it could really be anywhere within those squares, which can cover like 100 kilometers. So it really depends. But yeah, there is definitely significant uncertainty with determining the photype because of TESS's limited coverage. It also only covered about 50% of the area, so we were only able to map about 50%.
Okay, one more.
Awesome. So mine's related to the test instrument. You didn't really explain much about it. So you're just looking at a color composite. It's thermal. It's like what bands are you looking at? How is it telling us the photype? The test instrument effectively?
So let's see. It's mostly a thermally based system. So what we count on is we had to basically limit it to a certain time of day, which on Mars was like hour 6 to hour 18. And so we were able to limit it to that in order to get the best thermal coverage, so when the sun was up. So it does count highly on thermal. I'm not entirely sure on the exact science behind it, unfortunately. It's quite complex, but they do count on a thermal signature.
It's infrared.
Yes, or near.
All right.
Okay. Thank you.
Thanks, Molly.